Section 3.1, Derivative Rules. So far, taking derivatives using the definition has turned out to be pretty long and tedious, and it'd be really great if we had some rules that would allow us to make some shortcuts and figure out how to calculate some of these derivatives a lot faster. And in fact, there are some general rules, and we're going to figure out what some of them are in this section. And as you'll see, we're actually going to use the definition of the derivative to figure out what some of these rules are. So example number 1 says, consider the function f of x equals 2. This is a constant function. It's always equal to 2. Find f prime of x. So f prime of x, using our definition, is the limit as h goes to 0 of f of x plus h minus f of x divided by h. And remember, the way we calculate f of x plus h is we plug in x plus h in place of x here. And when we do that, we get 2, because it doesn't matter if you're plugging in x or x plus h, this function is always equal to 2. And similarly, f of x, that's just the function. It's still 2. So this is the limit as h approaches 0 of 2 minus 2, which is 0 over h. Now, 0 over h, if you divide 0 by any number, you're always going to get 0. So this is the limit as h goes to 0 of 0, which is just 0. Okay, so if f of x equals 2, then f prime of x is equal to 0. And this actually makes sense if you think about it. Here's the function f of x equals 2. It's just the horizontal line, and a horizontal line has a slope of 0. The derivative is slope. So it makes sense that f prime of x will give us 0. And in general, if c is a constant, say number 2 or 17 or pi, whatever that number is, if you take the derivative of that number, of a function that's just a number, you just get 0. So that's our first derivative rule. Next, we're going to calculate the derivative of x. So here we've got the function f of x equals x, and then f prime of x is the limit as h goes to 0 of f of x plus h minus f of x divided by h. And if I plug in x plus h up here in place of x, I just get x plus h back. So this gives me x plus h minus my f of x is just x. And that's all divided by h. The x's cancel, and I'm left with the limit as h goes to 0 of h divided by h, but h divided by h is just 1, and if you take the limit as h goes to 0 of just a number, you're always going to get that number. So this means that the derivative of x is just equal to 1, and one way of thinking about this, we're going to try to make some connections between the exponents of things like this and what happens with the derivative. In particular, x is the same thing as x to the 1 power, and we're saying that that's equal to 1, which another way of thinking about that is, well, let's just leave it at 1. I'll come back to it in a moment. And it's not too hard to check that if you take the derivative of x squared, you get 2x. In fact, we did that in section 2.6, I think. If you take the derivative of x cubed, you get 3x squared, and if you take the derivative of x to the 4th, you get 4x cubed. And we can see a pattern here of what's going on with the exponent, the original exponent, and then the coefficient in the derivative. And in particular, we can say that if you have the derivative of x to the n power, that exponent, either the 1, the 2, the 3, or the 4, is now going to come down in front. And what happens, what do you get for your new exponent? Well, you're subtracting 1 from what you had before. So we write this in general as the derivative of x to the n power is equal to n times x to the n minus 1 power. So here, this 1, another way of thinking about it, is it's 1 times x to the 0 power. Because x to the 0 power is just, x to the 0 power is just 1.